welcome to our lesson on double angle identities. So we're going to continue to add to the list of identities that we can use to evaluate expressions, to simplify expressions, to verify identities, and then ultimately later to solve. And the double angle identities that we're going to look at today are also super useful when you get to calculus. So before we talk about what the identities are, I kind of want to show you where they come from. It's not always the easiest thing to do, but if we have something that we can connect to, some prior knowledge, I like to try to do that when that's possible. So that's where we're going to start here. Where do these double angle identities come from? One of the ways we can see where they come from is by using some of the identities we talked about in the previous topic, which are the sum and difference identities. So we're going to consider the cosine of 2x. That is double one of our angles, so double our angle x, and this is going to lead to an identity. So when we consider this, what I would like you to think about is instead of the cosine of 2x, what if I was to call that the cosine of x plus x? Hopefully you would agree that that's the same thing. If I added those two x's, I would get two x's together. Well, now, hopefully you're recognizing that as the cosine of a sum. So yesterday may not be yesterday for you, but the last topic that we looked at was, again, our sum or difference identities. We said if we have the cosine of a sum, we just called it u and v, that would be equal to the cosine of u times the cosine of v, and then it's minus the sine of u times the sine of v. So if I replace all of those u's and v's with x's, so I'm going to put in x for u and x for v, then what we are going to be looking at here is the cosine of x times the cosine of x minus the sine of x times the sine of x. Well, when you multiply something by itself, it's considered squared. It's that thing squared, and so we can call this cosine squared x minus sine squared x. So that is actually one of our double angle identities, and you can see it in this box down here. If we have the cosine of twice an angle, it will be equal to the cosine of that angle squared minus the sine of that angle squared. Now the cosine of a double angle has a couple of different forms, and hopefully it would make sense why. Because this cosine squared, for example, we could replace. We know that cosine squared from our Pythagorean identity is 1 minus sine squared. So if we replaced cosine squared with 1 minus sine squared x minus another sine squared x, this just comes down, then we have two like terms there that I could combine. So I could also call this 1 minus 2 sine squared of x. And that would be a form that we see here. The cosine of twice that angle is 1 minus 2 times the sine squared of that angle. And then a third option would be, let me try to manage my space here. So in the sine squared minus cosine squared minus sine squared version, I started by replacing cosine squared. What if I replaced sine squared instead? So sine squared would be equal to 1 minus cosine squared. So I could also say that, let me just bring this down, leave the cosine squared this time, and replace sine squared with 1 minus cosine squared. And then if I distribute that negative, I'm going to end up with a cosine squared, a negative 1, and a positive cosine squared. So if I add the two cosine squareds together, I have 2 cosine squared, and then I have that minus 1. And that is the final form of my double angle or the cosine of a double angle. So all of these, the first one we derived just by looking at our cosine of a sum, and then by using our Pythagorean identities, we end up with some alternative forms. So the cosine of a double angle is going to be equal to cosine squared of that angle minus sine squared of that angle, or 1 minus 2 times sine squared of that angle, or 2 times cosine squared minus 1 of that angle. And those are, again, the three things we see happening here. So just using some of our prior knowledge, we're able to show exactly where the cosine of the double angle comes from. So now let's try this again with sine. And in fact, I think this would be a good place for you to pause the video and give this a try. We're going to consider the sine of 2x. Again, let's just say that that's the same as the sine of x plus x, so that we can apply our double angle, our sine of a sum identity. So the sine of a sum, I'll help you out here. So if we have the sine of u plus v, that's going to be equal to the sine of u times the cosine of v, and then a plus cosine u sine of v. So sine, cosine, cosine, sine, and again u and v in this case are just going to be replaced by x and x. So what we're going to be looking at here is the sine of x times the cosine of x plus the cosine of x times the sine of x. Now the order we multiply doesn't matter, so I'm going to leave this term alone for a second. But if I rearrange this and call this sine of x times cosine of x, it's the same thing. And then I have two like terms that I can combine. So sine, cosine, same terms. If I have one there and I add another, then I end up with two of those sine x, cosine x terms. Now, unlike the previous, where we could swap some things out using Pythagorean identities, we don't have anything we're going to swap out here for sine or cosine. So the sine of a double angle has just one form, and that's what we see happening here. If we're taking the sine of a double angle, it's going to be equal to twice the sine of that angle multiplied by the cosine of that angle. But then you can see how that comes directly from our sine of a sum identity. So the sine of our double angle equal to twice the sine times the cosine of those angles. All right, and then lastly, let's look at the tangent of a double angle. So again, let's call this the tangent of x plus x. So our tangent says if we're taking the tangent of a sum, oops, I wanted to change colors so this looks different. Let's call this the tangent of u plus v. Then that's going to be the tangent of u, and now I can't remember, and my power's out. Okay, so tangent of u, let me look here. Tangent, this is going to be a plus in here. Tangent of v, I'm trying to remember this formula. My power went out, so I'm a little distracted. I'm sorry. Sitting here in the dark is very awkward. Luckily, my iPad is charged. On the bottom of the fraction, it's going to be 1 minus tangent of u, tangent of v. So in this case, again, we're going to be swapping out u and v with x and x. And so we're going to be looking at the tangent of x plus the tangent of x. Good. So I make sure I got the formula right, sorry. And then on the bottom, we have 1 minus tangent of x, tangent of x. And so we have like terms in the top. If I have a tangent of x and I add another tangent of x, then I'm going to have two tangent of x's. And then on the bottom, I have 1 minus tangent being multiplied by itself, so that's going to be tangent squared x. Now I could possibly look for swapping some things out here, but the alternative forms for tangent aren't going to be as useful as the alternative forms for cosine. So we're going to stick with the tangent of a double angle being equal to twice the tangent of that angle minus, or divided by 1 minus tangent squared of that angle. And that's the identity that we see happening here. So each of the identities, the double angle identities, again, will be useful for simplifying, evaluating, verifying, but you can see how they directly come from our sum and difference identities, and how a little bit of swapping with our Pythagorean identities gets us some alternative forms. So let's practice using these identities. So we're going to try to use the identities first. In this situation, we are given that the cosine of an angle is equal to 2/3, and the sine of that angle is less than 0, Based on that information, we should be able to find the cosine of twice the angle, the sine of twice the angle, and the tangent of twice the angle. So the sine, cosine, and tangent of the double angles. So let's just try to draw out what's going on here. Hopefully that's intuitively what you're thinking to do with this information. If I have the cosine of an angle equal to 2/3, remember cosine is a ratio of the x value divided by the radius, unless we're in the unit circle with the radius of 1, but obviously that's not happening here. So we have a positive cosine, and it's saying here that sine is less than 0, which means it's negative. So if I have a positive cosine and a negative value for sine, that's what that's saying, then we have to be in quadrant positive x, negative y would be quadrant 4. So let's draw this out. Okay, if I'm in quadrant 4 with a positive x and a negative y, my angle is going to look like this. And so let's draw a triangle. Here's again my angle. Let's call it theta. That's what they called it here. I know that the x value here is going to be 2. I know that the radius length here is going to be 3. And I can use the Pythagorean theorem to find out what the y value is going to be here. So let me do that. If I have 2 squared plus y squared, it should equal the radius of 3 squared. So that's 4 that I'm going to have to subtract over from 9. So I know that y squared is going to equal 5, which y then has to be a radical 5. So radical 5 here, and because this y value, again, is in quadrant 4, we know it's got to be a negative. So I'm going to put a negative there and not lose that sign. Okay? So I think we're going to have all the information we need here to now find our double angles. So if I want to find the cosine of twice my angle theta, I'm just going to pick one of my versions up here to work with. The cosine of double my angle, it doesn't really matter which we use. Actually, if we look at all these, I may be getting ahead of myself. In order to find the cosine or sine or tangent of a double angle, I have to know the sine, cosine, and tangent of the angle itself. So cosine of the angle, sine of the angle, tangent of the angle. So let me go ahead and write those ratios before I get too much farther into this. So we were given, I'm going to run out of colors. We were given that the cosine of the angle was 2/3. And now I can also say that the sine of my angle, sine remember being a ratio of my y value over my radius, would be a negative radical 5/3. And the tangent of my angle is my y value over my x value. So that's going to be a negative radical 5/2. Alright, so now I think we're good. So let me just section this off a little here. So let's go with, first, let's try to find the cosine of the double angle. So the cosine of my double angle, again, you can apply really any of the formulas. I probably wouldn't use this one just because it's involving 2 of my trig ratios, and the other 2 look a little simpler for me, so maybe I choose this one, although all of them are going to be fine. If I want to do twice the cosine squared of my angle, I said the cosine of my angle is going to be 2/3. So from the cosine of my angle, I'm going to plug in 2/3, but remember that's squared. So it's twice the cosine of my angle squared, that's what I have here, and then a -1. So the trig part is done. This is just a little bit of arithmetic to deal with here. So we're looking at 2 times 2/3 squared is going to be 4/9. And that's going to be technically 8/9. And if I subtract 1, then I'm subtracting 9/9. And so I end up with a -1/9. And if you want to use your calculator to do some of that work for you, that's totally fine. And I'm going to confirm just because I'm sitting here in the dark and I don't know. Square that, subtract 1, make it a fraction. Good, -1/9. Yay. My brain's still working, sitting here in the dark. Okay, so I got the value for the cosine of twice my angle. That's going to be the first part of our answer, so I did this one. And now let me change colors. Let's do the sine of the double angle. So the sine of the double angle, only one version of the formula here. It's 2 times the sine of the angle times the cosine of the angle. So 2 times the sine of the angle, I said right here, was negative radical 5/3. times the cosine of the angle. We got that right here. That's going to be 2/3. And now again, just a little bit of arithmetic. So on the top of this fraction, the 2 times the negative radical 5 times the 2. Well, 2 times 2 is 4, so it'll be a negative 4 times radical 5. And on the bottom, we'd have 3 times 3, which is 9. Isn't anything we can do to simplify that. So that's going to be the exact value for the sine of my double angle. And then lastly, I'm going to do the tangent of the double angle. So the tangent of my double angle. On the top of the fraction is twice the tangent. So tangent, we said over here, was going to be negative radical 5 over 2. And then that's going to be divided by 1 minus the tangent squared. So negative radical 5 over 2 squared. So again, it's arithmetic from here. On the top of the fraction, we're looking at negative 2 radical 5 over 2. So just multiplying there. On the bottom, I have 1 minus, I'm going to square the negative radical 5 over 2, which is going to become a positive. On the top of the fraction, radical 5 times radical 5 is going to be 5. On the bottom of the fraction, 2 times 2 is going to make 4. So again, just a little more arithmetic. Let me leave this negative 2 radical, actually, I don't even know why I did that. It's kind of silly. I didn't recognize, I don't know why I didn't see it. But right here, I can reduce those 2's out. So let me just back up a little bit. I can do that. I even wrote the 2 over 2 and was like, oh yeah, let's leave that alone. So I can reduce. Multiplying and dividing by 2, those are opposites. So I know that this is just going to be a negative radical 5 in the top, which looks much better. And now let me continue. So a negative radical 5 in the numerator. What the heck? There's a stray gray or green mark over here. Negative radical 5 in my numerator. In the denominator, I have 4/4, and I'm going to try to subtract 5/4, which is going to leave me 1/4. So I'm looking at a limited amount of space. I have negative radical 5 in the top. On the bottom, 4/4 minus 5/4 is negative 1/4. And so negative negative is going to make our answer positive. Dividing by 1/4 is the same as multiplying by 4. So we're going to get a positive 5 in front of the radical 4. And that's going to be the exact value there. So tangent of 2 theta, tangent of our double angles for radical 5. Now I just want to point out, because why not, that there's another way we could have found the tangent. I need another color. Let's pick orange. That tangent we also know is a reciprocal of sine over cosine. So if I wanted to say that this was the sine of the double angle divided by the cosine of the double angle, that would be another alternate way for me to figure this out, since especially I've already found my sine and my cosine. So if I took negative 4 radical 5 over 9, which is what I got for my sine of my double angle, and divided it by negative 1/9, which was the cosine for my double angle, again, the negatives are going to cancel, the 9's are going to cancel, and we're going to end up with the same 4 radical 5. So that's another option if you don't like that tangent double angle formula, and you already have the values for sine and cosine of the double angle. Okay, so not necessary to do it both ways, just want to show you that you have options. Okay? That's a lot of work for one problem. I might not necessarily ask you to do all of those things in one problem. Like if you're taking your quiz on Friday, then, maybe just one of those. But old information connected to new, and hopefully you can see why some of that is useful. Alright, so let's continue. We're going to work in reverse on the second example. It says to find the values of the 6 trig functions, which means find the sine, find the cosine, find the tangent, secant, cosecant, cotangent of theta. So just like we've done before, finding the 6 trig function values. But this time what we're given is that the cosine of twice our angle, our double angle, is 4/5. And it says our angle is between 90 and 180 degrees. So that, go back to my presets here, this means that our angle, if we're between 90 and 180, is in quadrant 2. And we know the cosine of our double angle is equal to 4/5. So we want to apply one of our cosine formulas here and do a little bit of solving. So one of our cosine double angle formulas. If we go back here and look at these, I don't know that I would use this one to solve, because what I'm going to do is replace this with 4/5, right? So if I make this equal to 4/5, I'm not going to be able to solve because I have sine and cosine in there. It's like trying to solve one equation with an x and a y. It's not going to work. So I'm going to pick one of the others. Let's just say I choose this one. Okay, so I'm going to say that this is equal to, instead of the cosine of the double angle, it's equal to 4/5, since those two pieces were given to me as equal. Okay, so I'm going to use that second identity. Oh, I'm like, why isn't this going? Because my eraser's on. So we have the cosine of our double angle equal to, I already forgot, 2 times, which one I wanted to use, the cosine squared of the angle minus 1. So we're going to say, for this situation, that 2 times the cosine squared of our angle, which is called theta, minus 1 has to equal what they give me here, is 4/5. And then I'm going to do a little solving for theta. So if I'm solving this, just like solving for x, I want to undo the operations like the minus 1 by adding it over. So let me add 1 to both sides. That's going to give me 2 times the cosine squared theta equal to 4/5 plus 5/5. Right, 1 is 5/5 is going to give me 9/5 over here. Alright, then I want to get rid of the multiply by 2 by dividing both sides by 2. So those are going to go. And now I have the cosine squared theta equal to 9/5 divided by 2. Remember, that's 9/5 multiplied by a half. So that's going to give me 9/10. And then lastly, so I got rid of minus with plus, got rid of times with divide. I'm going to get rid of the square by taking the square root. So I'm going to end up with the cosine of my angle equal to technically a plus or minus. The square root of 9 I can take to get 3. I can't take the square root of 10, so I have 3 over the radical 10. And eventually we'll rationalize, but I don't want to deal with that just yet. Because we need to decide, are we going to keep the positive or negative version? Now remember, we're in quadrant 2. In quadrant 2, our cosines, our x values, are negative. So in Q2, cosine is negative. So we're going to say the cosine of our angle is a negative 3 over radical 10. Okay, so we know the cosine, that's one of the 6 trig function values we're looking for. I would say at this point we should probably draw this out. Although, if we wanted to, gosh, there's so many options. I'm not sure which one I want to show you, but I'm going to draw this out just because, again, we can relate this back to something that's familiar. If I now draw this out in quadrant 2, my angle, here's my angle in quadrant 2. Let's make a triangle out of this. Again, here's my angle, theta. We just said that the cosine would be negative 3 over radical 10. Remember, cosine is x over r. So I know my radius is going to be radical 10. I know my x value is where I have that negative 3. And again, I can use Pythagorean theorem to figure out what that y value is. So y squared plus the negative 3 squared is going to equal radical 10 squared. So the negative 3 squared, why'd I put an equal, is going to make 9. Radical 10 squared is going to make 10. If I subtract the 9 over, then I see y squared equal to 1, and then I take the square root, which means y has to equal a 1. And positive because, again, we're in quadrant 2. So let's put the 1 there. And now, again, I think we have all the information we need, and there might have been some other paths to take, as I was waffling with earlier. But let's go ahead and write out the values for our 6 trig functions. So let's say we want the cosine of our angle, and then the sine of our angle, and then the tangent of our angle, and then we'll flip all those over, get the reciprocals in just a second. So cosine, actually, that's the one we solved for over here. We said was going to be negative 3 over radical 10. Well, we should really rationalize that. So let's make it negative 3 radical 10 over 10. And then the sine we know is a ratio of our y value over our radius. So that's going to be 1 over radical 10, which will be radical 10 over 10 after we rationalize. And then the tangent is a ratio of our y value over our x value. So that would be 1 over negative 3 or negative 1/3. And now we can easily find our reciprocals. So the reciprocal for cosine is going to be secant of our angle. And maybe we flip the unrationalized version, which we had over here. So we're looking at negative radical 10 over 3. Reciprocal for sine is going to be cosecant. So the cosecant of our angle is, let's again take the unrationalized version, so just a radical 10. And then the tangent, reciprocal is going to be cotangent, and the reciprocal of negative 1/3 is going to be negative 3 over 1. And we did it. There's the value for all 6 of our trig functions. And look at that, I had plenty of space, but maybe I'm writing smaller than you might be writing. And zooming in and out is also very helpful. Okay, so we can use our double angle identities to solve for the angles or the trig functions of the angles as we did here, or we can also use information we know about the angle to find the double angle, so it works in both directions. Not only can we use the identities to do some solving and finding of trig functions here or evaluating, we can use it for simplifying. So let's try that. When we see some of these situations, we just have to recognize that we have a double angle. So when you're seeing this, hopefully it's looking familiar. If you look back at our first cosine of a double angle, cosine squared minus sine squared, this piece right here, that's what we're seeing. So then we're going to, instead of expanding out a double angle, we're going to try to simplify or condense this. So our formula, just to bring that here and not have to page flip, says if I have the cosine of twice an angle, that it's equal to the cosine squared of that angle minus the sine squared of that angle, right? So I'm calling the angle A in the formula, but in the picture we're seeing, A is going to be replaced by 7x. So this is technically A here and A here. So if I was to condense this, I can say that the cosine squared of 7x minus the sine squared of 7x is going to be equal to the cosine of, I'm going to go back to this part here to condense again, the cosine of twice our A, which we said is replaced by 7x. And so this is going to simplify to the cosine of 14x. So it's kind of using that formula in reverse. And that would be the simplified form there. So sometimes we end up with an expression that still contains a variable. And you can see here, number 4, we don't have any variables, so we're going to end up with a numeric answer this time. So twice the sine and the cosine of an angle. Again, hopefully it's looking familiar. We have twice the sine and a cosine in the sine of our double angle. So again, the formula we're going to apply here says if we have the sine of a double angle, it's going to be twice the sine of the angle times the cosine of the angle. This is exactly what we see right above, but in place of A, we have 15. So I'm going to replace this part now. I'm going to say this is the sine of 2 times 15, and there should be degrees in here. I forgot to type those in. So this is really the sine of 30 degrees, and the sine of 30 degrees, we know that comes directly off the unit circle. Remember the unit circle, on the unit circle, a 30-degree angle intersects at the coordinates radical 3 over 2 and 1 over 2. That's right there in your left hand if you're using the hand trick. And the sine is the y value in that coordinate. So the sine of 30 means we can go one more step here and say this is going to be exactly equal to a half. And I used pink. Let me try to be consistent. There we go. Okay, one more for you to try. If you want, pause the video if you're feeling pretty confident about this. If not, let's figure this next one out. So again, we've got cosine, 2 times cosine squared of some angle minus 1. Again, hopefully that looks familiar. That's going to be one of the cosine of our double angle identities. So the formula says, was I doing blue? Try to be consistent. The formula says that the cosine of a double angle can be equal to twice the cosine squared of the angle minus 1. Now what we see in this picture is the angle, or A, the variable, replaced by 157.5 degrees. So now I'm going to replace this, use that condensed form, replace A with that same amount. So we're looking at the cosine of twice 157.5, again, degrees. So that's the cosine of, You're really pushing me here. I'm not going to even try it. I feel like I can, but yeah, okay, just making sure. That's the cosine of 315 degrees. Now that's another angle that's on the unit circle. The reference angle is 45 degrees. So I know the reference, this is just, if you want to just look at your unit circle, that's totally fine. But in my head, I am remembering the reference angle is 45 degrees, which means the coordinates where it intersects the unit circle would be radical 2 over radical 2. Now 315 degrees is going to be in quadrant 4. That's where we have positive x's, negative y's. So 315 degrees is going to intersect the unit circle here. If I want the cosine, I want the x value. So I'm going to go one more step here and say the cosine for 315 is going to be a positive radical 2 over 2. And that's a lot cleaner than the version that we started with, okay? So if you are simplifying an expression, if there are no variables like in the first one we looked at here, if we have variables in what we're starting with, then we should have variables in what we end with. But if everything is numeric, so we have no variables here, we have no variables here, all numbers, all numeric, then we end up with those numeric answers, okay? So we got one more and then we're done. It says use the double angle identities to verify an identity. So doing some verifying, we're given that this is an identity. That means no matter what variable or value of the variable we plug in, we should get the same thing on both sides. So we're going to take one side and try to simplify it down till it looks like the other. So for me, it doesn't really matter which side. I'm looking at this thinking the left side has more places for us to make some substitutions. So let's do it. Let's say cotangent. We can swap that out. Cotangent we know is going to be cosine over sine, and that might not be necessary, but let me do it. The sine of our double angle we said is going to be twice the sine of the angle times the cosine of the angle. So then where could we go? Well, this is technically over 1, which means that the sine, the common factor of sine, can be reduced out of this. And so what we're looking at in our numerator is cosine of x times 2 times cosine of x. So technically that's 2 cosine squared x. And the denominator just has a 1, which means we're not really having to worry about that denominator. So cosine squared, let's see. Cosine squared, we could swap that out. Cosine squared could be 1 minus sine squared. And then if I multiply out the 2, I suppose, I could call this 2 minus 2 sine squared. Yeah, I don't know that I'm getting anywhere. So again, this is going to happen to you, so don't worry about it, but it appears that I'm stuck. So what do we do when we're stuck? Erase it, start over, skip it. No, they're all good options, but let me go to the other side and see what I can do. So on the other side of this, I'm going to bring down the 1 because I can't mess with that. But I have the cosine of 2x. Now this is a little tricky because cosine has a lot of different forms. So let me go back and see if any of the forms maybe looks like something that I have in here. So if I go back and look at my cosines, 1 minus 2 sine squared, or 2 cosine squared minus 1. Let's see. 2 minus, oh, that looks kind of close. I'm sorry about the page flipping. 2 cosine squared minus 1, or 1, is that the one I had? Cosine? Now I can't even remember. Oh, sine squared. Okay, so let me attempt to replace the double angle with 1 minus 2 sine squared. Okay, so 1 plus cosine of the double angle, I'm going to go 1, geez, I lost it again. It's up here. 2 cosine squared minus 1. So I'm going to replace this. Oh no, I don't want to use the cosine one. I want to use the sine one. I'm so sorry. I told you my power's out and I'm losing it. I had this on a separate screen for myself so I didn't have to keep looking back and forth, but my screen is dead, so that is not helpful. So I'm going to go 1 minus 2 sine squared. I'm so sorry about the page flipping. 1 minus 2 sine squared x. Okay, so the 1 came down, and then this got replaced with this. That's what happened there. And now we're in good shape because if I add the like terms here, the 1 and the 1, then I end up with 2 minus 2 sine squared, and so we're good. Let me just kind of draw a line to separate. Now that looks terrible. But let me get rid of this because I don't need it. So on the other side, I got stuck at this point here. So I went to, or on the left, I got stuck with 2 minus 2 sine squared. So then I went to the right and did some swapping out there, and I ended up at the same stuck place, which is good. Because if we want to verify, we just need one side to get to match the other, and we did that. So we had to use 2 double angle identities, but it all worked out. Okay? So hopefully you got enough to go work on your homework. I hope your power is on and you're not sitting in the dark in your house. If you have any questions, please reach out. But until next time, take care.